We'll be talking about how to find the area between curves in this video. But before we begin with how to find the area between curves, we will review integration and how to find the area under one curve. First, we'll review integration. To find the definite integral of a function, you must first integrate the function. We'll use the integral of 3x squared from 1 to 3 as an example. To integrate 3x squared, we add 1 to the exponent and divide by the number of the new exponent. We are then left with x cubed. From there, you substitute the upper limit, 3, into the integral. You then substitute the lower limit, 1, into the integral and subtract this answer from the first value. The number that you are left with is the answer for your definite integral. When finding how to find the area under a curve, there are two methods that you can use. The first one is using approximation using rectangles, and the second is integration. It is important to understand how to use integration because that's what is used when finding the area between curves. So when we are finding the exact area under a curve, say y equals f of x from x equals a to x equals b, we use the definite integral area equals the integral of f of x from a to b. Be careful that you don't switch the a and b. Switching these will give you the negative answer of your actual area. Let's say that big F of x is equal to the integral of f of x. From there, you take big F of x from a to b, giving you the equation big F of b minus big F of a to give you the area under the curve. The area under a curve is simply the definite integral of a function. We'll use a simple function as an example to show this. We will use the integral of 2x dx from 1 to 4. Here you can see what part of the graph under the curve we are finding the area of. Integrating this equation, we get x squared. Taking the definite integral from 1 to 4, we get 16 minus 1, which is 15. The area under the curve 2x from 1 to 4 is 15 units squared. Now we'll talk about actually how to find the area between two curves. The overarching idea is to find the area under the curve that will produce a smaller area and subtract it from the area under the curve that produces a larger area. These are usually obvious when you draw the graphs. For curves parallel to the x-axis, the larger curve will be the one that is highest when the y values are positive, and the lowest when y values are negative. For curves parallel to the y-axis, the larger curve will be the curve that is farthest to the right when the x values are positive, and farthest to the left when the x values are negative. Looking at a graph with two random curves in a given interval, we can see which curve is the bigger curve, the top one. The yellow highlighted area under this curve represents a larger area. Now we'll illustrate the area under the smaller curve with a pink marker. The goal is to just find the area of the remaining yellow highlighted area. To do this, we must first label the curves, the top one with the yellow area being g of x and the bottom curve with the pink area being f of x. The interval for which the area under the curves are shown is from a to b. So how do we find just the yellow part and not include the pink part? To do this, we must first find the area of the yellow before the pink was added. Then we must find the area of the pink. To get the remaining yellow areas alone, we must subtract the pink area from the entire yellow area. This will give us the remaining area of the yellow. Mathematically speaking, this represents the equation of the integral from a to b of g of x minus the integral from a to b of f of x. This is the equation to find the area under the curves when they're parallel to the x-axis. The integral from a to b of the upper function minus the integral from a to b of the lower function. It is basically the same for functions that are parallel to the y-axis. Here we have the entire area under the curve in yellow, adding the pink to again represent the remaining yellow area, which is equal to the area between those two curves. Instead of an upper or lower function, the equation for these examples is an integral from c to d of the right function minus the integral from c to d of the left function. Make sure you change the a and b in the definite integral to c and d, representing the values on the y-axis. You must also change your functions to be in terms of y. If you forget to change your function to be in terms of y, you will have to use two functions because the upper curve changes at the point of intersection. Now we'll do an example of finding the area between two curves using the points of intersection. Using the curves y equals 4 minus x squared and y equals negative x plus 2, find the area between the curves on the interval negative 2 to 3. First, we'll draw the curves on a graph to see where the curves intersect as well as to see which curve is the upper function. Now that we have our graph, we see that the upper function switches. From negative 2 to negative 1, the upper function is y equals negative x plus 2. From -1 to 2, the upper function is y equals 4 minus x squared. And from 2 to 3, the upper function is y equals -x plus 2. These are important to take notice of because it'll help us when we set up our integrals later. Because the upper functions change through our interval, we must use the points of intersection for our intervals. To do this, we can either set the functions equal to each other or use our calculator to find them. Because our functions are simple, we'll set them equal to each other to find the points of intersection. When we set 4 minus x squared equal to -x plus 2, we simplify the equation to get x squared minus x minus 2. We then factor that and get our points of intersection to be x equals -1 and x equals 2. Now that we have our points of intersection, we can find the definite integrals for each interval. For the first area from -2 to -1, our upper function is -x plus 2. Our equation is a definite integral from -2 to -1 of -x plus 2 minus the definite integral from -2 to -1 of 4 minus x squared. Our next interval is from -1 to 2, our upper function being 4 minus x squared. Our equation for this interval is a definite integral from -1 to 2 of 4 minus x squared minus the definite integral from -1 to 2 of -x plus 2. The last interval from 2 to 3, our upper function is -x plus 2. For this equation, we get the definite integral from 2 to 3 of -x plus 2 minus the definite integral from 2 to 3 of 4 minus x squared. Now that we have the equations for all three areas, all we have to do is add each one together to get the total area between the curves. Here's the equation for adding all of the areas together. To solve this equation, we can either do it by hand or use a calculator. We are going to use a calculator to save a lot of time. Plugging this into our calculator, we get 49 over 6, or 8.167. In this problem, people may subtract the last area, the area from the interval 2 to 3, because it appears to be negative, being in the fourth quadrant. But because we are finding the area between two curves, there are no negative areas. Wherever the areas are between the curves, they won't be negative. Before we end, I wanted to go over a few key points for finding the area between curves. The first one is to always find the points of intersection of the two curves in order to set up the intervals. The second is to remember to change your functions to be in terms of y when the curves are parallel to the y-axis. And lastly, a common mistake is to square the areas between the curves. This will be volume. The definite integral itself is the area under a curve. There's no need to square it. Thanks for watching this video, and I hope you check out the worksheet and practice it for yourself.